Welcome back. In this lecture, I'm going to briefly review the assumptions of linear regression. As I've mentioned in my other videos on linear regression, that before you start to think about deploying linear regression or any sort of statistical model or machine learning algorithm, it's very important for you to review your data and know what type of data you're working on, and most importantly to make sure that the test or the model that you're about to run actually meets the assumptions for that particular model. Meaning, if you do not meet the assumptions, then you're more likely to produce errors or have biased results or have inaccurate model. Therefore, it's important to do preliminary uh, assumption review or testing of your data to make sure that it's the best fit for the model. For the linear regression, there are several assumptions that are listed by the academics and the practitioners. The most important ones are listed here. Uh, the assumption tests or assumption models ranges between 4 to 7. So the most important ones I've listed here, I'm going to briefly review them with you and kind of provide you high level details or what they are. I will have particular videos on how to use programming tools to actually perform each of these actions to attain assumption results. To begin with, the linear model for the linear regression test, it's important that our data, our variables are linear. Otherwise, linear regression may not be the right test. And what I mean by that is, let's suppose that, excuse me, we have two variables of x and y, where x is our independent variable and y is our dependent variable. And if we plot the data values or data points uh, where each of the data are placed, and if we have a pattern like this, then this is not a linear model. This is not a linear trend. Therefore, maybe linear model analysis may not be the right test for this because there's actually no pattern at all, or even there are a variety of other nonlinear regression models, including quadratic, logarithmic, exponential, uh, etc. Type of models that we can use depending on our data shape once we scatter the block. So that's the first assumption, as I said, that is important for us to make sure that both of and that our data are actually linear. And an example of a linear could be, where we have data points all scattered like that. And if we draw the this fit line, you see that it's linear. There's a linear shape to it. So that's very important that before we even start an analysis, that we check the shape of our data by creating a scatter plot where we look at each of the data points. That's the interaction of both data and and then see how that shape looks like, and then make a decision based off that. The sec, let me put a check mark here. Oops. The second one is no endogeneity. So the endogeneity and selection are key problems for data analysts and research on inequality. Technically, endogeneity occurs when a predictor variable, for example, x in a regression model, is correlated with the error term in the model. This can happen and there are a variety of reasons, of conditions. But two cases that are especially common in inequality research is the first one is the omitted, what we call omitted variables or omitted variable bias. So omitted variable bias is, as a matter of fact, let me just write this down. Omitted variable bias is when we actually uh, 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 do not count or disregard a variable that's important for our analysis. variable bias. That's the first one. The second one is the when the outcome variable is a predictor of X and not simply a response to X. And it's called simultaneity bias. So simultaneity bias. So as a data analyst, again, you're not only uh, running or applying a model, but you're also kind of looking at the background of your data, of your research, and take on the role of the subject matter expert or someone with the knowledge of the domain to understand not only the data from its shape and pattern, but also to understand what are the mechanisms that led to the data, to make sure that there's no any bias, especially any omitted variable bias, that we're looking at the right variable to look at the right prediction. Otherwise, we're creating the most important biases in it not only that will not only affect our research result, but also our prediction model, which are the omitted variable bias and simultaneity bias. And so, therefore, it's important that we brainstorm and determine and decide on our independent variables before even again starting to deploy any analysis. And the third assumption is the normality and homostaticity of our data. So normality, it's important that we assume that we have equally distributed observation for the range of our predictor. So at the end of the model training, the predicted values, each test data should be a normal distribution. So, in other words, we have to make sure that our data are normally distributed or normal. Otherwise, again, we will be running and we will be producing inaccurate model. Uh, so once one can get an idea of distribution of the predicted values by actually using a variety of tools and techniques, one of the ways is to plot a density or a QQ plot to actually a QQ plot actually provides a type of plot that shows how that let's say that shows kind of a line where the QQ plot where you can see the data and how they vary, and you can make a decision based on that if your data is normal or not. You can also look at the shape of your data by looking at a histogram, right? Where you can see if your data distribution is something kind of either a bill curve distribution, symmetrical distribution, or something close to it. You can also use what we call uh, 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 we can also use statistical tests to check statistically if your data are normally distributed or not. There are a variety of methods that you can use to establish if your data are normally distributed or not, but you can start from visualization of graphs and then work your way toward running statistical tests. And on the other hand, homostaticity or homogeneity of variance is an assumption of equal or similar variances in different groups being compared. So this is an important assumption for parametrical statistical test overall, either it's t-test or ANOVA, any test that operates based on the assumption of parametrical test, because they're sensitive to any outliers or dissimilarities. So even uneven variances in sample result can result in bias and skewed test results. So it's important that we understand that there's no the similarities and variances that actually produce very biased result that we actually thought was a significant difference, while that difference does not come from the actual test, but it comes from variance discrepancies. So that's very important. So the homogeneity of variances again is a very important component uh, of assumptions any type of test that involves working with parametrical studies or parametrical models. Parametrical models are any model that have that are measured based on their averages, or that can be highly affected by any data that's like highly skewed. So I hope this part is also understood. And the other part is multicollinearity. So if the predictor variables are correlated among themselves, then it is called a multicollinear. Is said to have multicollinearity problem. But why is multicollinearity can be a problem? The answer is that high collinearity means that both of the variables vary very similarly and can contain the same kind of information. So this type of potential issue can lead to redundancy in the data set. So and because of the redundancy, only the complexity of model increases. So no new information or pattern is learned about the model. So we try our best not to let that happen. We try to avoid data that are highly correlated or have a highly correlated feature while we create models. Simply we just don't want to look at the same data that were listed twice. So that's what it's all about. And the next one is the autocorrelation. We also want to make sure that there's no autocorrelation. So autocorrelation is one of the critical assumptions of multiple linear regression. Says that there should be no autocorrelation in data as well, just like multi-collinearity. So this is actually when the residuals are dependent on each other, then there's autocorrelation. And this factor is visible in case of, let's say, stock markets, or when the price of stock is not independent of its previous one. So plotting the variable on a graph like, let's say, or a scatter plot or a line plot allows you to check for any autocorrelations in terms of ups and downs, or however you want to term it. So, and that's again that has to do with the residuals. So we want to make sure that there is no autocorrelation in our data, and that when the residuals are dependent on each other, then that itself is indication that there is autocorrelation existing within the data set. The last one is a basic assumption that we want to make sure that our data is independent, or it's unique. It's unique and it's also independent of the other observation, meaning each observation of data should be measured separately on a unique measurement, or that one observation does not cause any effect, or does not is not caused by another observation. So the uniqueness of the data within each of our variables is also very important. This was it for assumptions of linear regression. So although these assumptions are to be met, but there are ways to actually transform for many of these assumptions. For a few of these assumptions, there are no solution. We may end up having to use a different model that meets our that meets the standard of our data, or that meets the requirement of our data model based on its shape and all these characteristics. But in some cases, we may be able to kind of pass a solution. For example, for the normality, we can transform the data, or we can do a logarithmic transformation of the data. We can use like logarithmic transformation or any other type of transformation to transform the data to be able to meet the standards of our model. This is it for this subject for today. Until next time, thank you for your time and have a great day.